Good morning, guys.
Morning.
Morning.
I see only a few people showed up today, and I think we're toward the end of the course, and a lot of people are getting more and more tired. Let me promise the following, okay? In about 2 weeks, this whole thing will end, okay? So again, we are still finishing. Okay, we probably should do something when this thing ends. I know we never met. Probably we should meet on campus and maybe do something, play soccer or something. Okay. Okay, so we are still finishing water balloons. Oh, okay. Yeah, okay. That should be fun. Anyway, we are still finishing chapter 42 actually, because last time I introduced the idea of Fermi energy level, which is an important concept that you guys really need to be familiar with. And it's actually one of the objectives of this class, as I was saying before. You really need to know that formula on how you find the energy, the Fermi energy level. It's really related to within a constant, like number 12 or something like that, to the density of charge carriers, namely the electrons in the case of conductors, and times some power in there of 2/3. Okay. Other than that, all the other are just basically numbers. And then there is another factor also in the denominator, namely the mass of the electron, and of course the square of the Planck's constant. So other than that, that's the other things are just numbers, 2 and pi and 3 and all of these things that you can throw in there, okay? But of course, for exams purposes and for testing purposes, you really need to know the formula for that. And that has an implication not just on the solid state physics, which is critical actually to understand solid state physics. We will see actually the nucleus also for the atom can be actually modeled also using the free particle or the particle in a box model, with the exception that we are not treating the electrons there at all, because there is no electrons inside the nucleus, but actually the nucleons themselves, namely the protons and the neutrons. And we follow a similar approach actually, and we find the different energy levels that are inside the nucleus, and they will be quantized also in a similar fashion. So this is, and we will find actually the Fermi energy level 2 there for the nucleus. And obviously, in the case of the nucleus, it takes far more energy to destabilize it than just those few micro electron volts. I mean, it's of the order of a mega electron volt. So it's about 1 billion times more energetic than the case of the so in other words, thermal agitations are not really going to get anything outside of the Fermi energy level. So that's the point being. So you really need to have some high energy gamma rays or some other processes to destabilize the nucleus. So I'm talking ahead a little bit for chapter 43, okay? So this is how, if you wish, the connection between 42 and 43 is. As a matter of fact, solid state physics and elementary particle physics are one of the most advanced branches of physics, and probably all of science altogether. So before we get into nuclear physics, though, we still have the idea, since let me share with you a screen. Let me find the topic first. Share. So let me basically summarize what we did last time, because probably it was a little bit too much. So what we said was, we took the case of a conductor, and basically because of the overlap of the valence band and the conduction band at that point, with any kind of thermal agitation, I will have plenty of electrons that are free to move. Okay, and this led to a little bit of something that made me thinking after the class that probably I confused you a little bit with something that you learned from physics too. Okay, namely temperature has, I mean, I may have given you the impression with the rise of temperature, the resistance somehow will get less and less, and that's not true for conductors. That's what you saw in physics too, that it is not true. That with the rise of temperature, the resistance actually increases, does not drop. As a matter of fact, the current decreases because of the fact that the material becomes more resistive. And if we go back to Ohm's law, which says that basically the current is inversely proportional to the resistance, as the temperature increases, in that case, what happened as the charge carriers are moving inside your conductor, they will be colliding more and more often with themselves and also with the ions basically that they are part of. And at the end, that will increase the resistance because the time between collisions, tau, actually is shortened at that point. Okay, and the conductivity is proportional to tau, which means that the resistance in this case will increase because tau is getting less and sigma is getting less. So this is something that you have seen in physics too, okay? And this is not dismantled, so this is still true. What I'm trying to say in here is that with the when you have the energy bands, basically at that point they merge, and for the conductor, it's for the conductor at the Fermi energy level, at T equal to 0 Kelvin, at that point, all of the states are filled. Okay, but this is actually a theoretical limit. This is not practical. You can never get a T equal to 0 Kelvin. You can get a 0.000001 Kelvin if you like, but this T equal to 0 Kelvin is an idealized situation. It doesn't exist. And there is a law in thermodynamics that we didn't really talk about, and it's called the third law of thermodynamics. So remember, we explored the zeroth law, the first law, and the second law. But there is actually a third law of thermodynamics that deals with this specific item that tells you that you can never reach 0 Kelvin, okay? Because the law says basically that the entropy will become 0. And if the entropy becomes, this is the absolute value of the entropy, not delta S. And this is not possible. Okay, so that's basically what the law was. But this law now is really useless in the advent of quantum mechanics because of the fact that you cannot reach it, period, because of the Heisenberg uncertainty principle. So now you really don't need this law. That's why we didn't really talk about this one. And which brings me to the point that when we did our analysis and we said that T equal to 0 Kelvin, at that point, what we are talking about is that all of the states below the Fermi energy level are filled, is really an idealized situation because we know it doesn't exist, okay? So with the slightest change in temperature, which is the case, you will have plenty of free, basically, electrons that can jump in the next levels, and they will be free to roam. Okay, so that's what I meant with it. I didn't mean that the resistance somehow drops with the higher values of temperature, meaning as I increase the temperature, I'll have more and more available electrons to move, which give me the impression that somehow I got into a situation where I have R becoming less and less, and that's not true. Okay, so I hope to have clarified this point in here so that you don't go with the impression that somehow the resistance is going to be less for the case when temperature is increased. As a matter of fact, for normal conductors, the resistance will go higher with the increase in temperature, which results in currents being lower, as you have duly seen in physics too. Make sense?
Yes.
Yes. Okay, very good. So I know that you have had this discussion probably in detail in physics too, so I didn't want to have that confused. So let me go back a little bit onto that model of the Fermi sea and revisit it a little bit, because we're still dealing with conductors at this point, normal conductors, basically copper and iron and what is it, gold and all of the other stuff in there, okay? So basically what we saw there is that the Fermi energy level is quantized, and it has 3 quantum numbers, nx, ny, and z. And it's usually given by h bar times some value of k in this case, and k happened to be, k squared actually has to be with n squared plus another n squared plus another n squared. And this n squareds are actually in the respective directions, okay? And also, I took the case of symmetrical cube. You don't have to. You could have taken it to be in not symmetrical. So you could ended up with the different width and depth and height of that cube. So each one of them is corresponding to the direction. And of course, times pi squared, okay? So this is where the K number is, because there is a quantization that gives me that condition on the boundary conditions, okay? And divided by, of course, twice the mass of the electron in this case, okay? So this is the energy that depends on all of these numbers, okay? And the way I represented it, because these numbers are strictly positive, nx, ny, and z, is that I went to the n space. We really did not need to operate in the n space, in the space of the integers, if you wish. We could have operated in the space of the K space, the wave number space itself, okay? We could have operated in this wave number space. And then in this case, the distance on the x-axis in here, this is the kx direction, the direction that is corresponding to this number. So the distance between them is actually going to be, when nx is equal to 1, this is going to be pi over lx. And this is going to be, with the next one is actually going to be 2 pi over lx, or the distance is going to stay pi over lx. The distance between this number and that one is always going to be pi over lx. In other words, I could have a pi over lx, that's for nx equals to 1, or a 2 pi over lx, that's for nx equals to 2, or a 3 pi over lx for nx equals to 3, and so on and so forth. So this is one way of looking at it. The same thing, let me try to, the same thing in the y direction, I would have in here, in this case, pi over ly, and in this case, pi over lz, still ly, the distance is the same, and the same thing in here, pi over ly. So in other words, this is pi over ly, and the next point is twice this number. That corresponds to ny equals to 2. And the third one is going to be 3 pi over ly, and so on and so forth. So this will be your ky, and this will be your kz, and in this case, the same thing. Again, this distance is pi over lz, and this distance is pi over lz, and so on and so forth, okay? So I hope that you guys get the picture. And if I do this argument and follow it, basically, I can form any cube you want to in the K space. So this is in the wave number space. Okay. And any cube, you take it in space, is going to have a side on the x direction, which is pi over lx. And in the y direction, or in the z direction, is going to be pi over lz. And in the x direction, the y direction is going to be pi over ly. Okay. So it's going to form a cube of the similar, of the same, of this sides. Not necessarily a cube. I don't know what you want to call it, okay? When you have the sides are not the same. So it's not necessarily a cube. So we took the case of the cube. But the point being in here, it works for any geometry in this case. You don't have to have, it works even in the case of the degenerate, because that case, non-degenerate case, basically, when the degeneracy is lifted by the case when we don't really have symmetry. So when we did the argument, it was actually for a degenerate case where Lx equal to Ly equal to Lz equals to L, okay? So I have a cube in this case, so I can find the volume of this cube, and the volume of this cube is simply equal to pi cubed over Lx times Ly times Lz. And that is going to be equal to pi cubed over the volume itself, because then it doesn't matter, because the product of the width times height times depth is going to be always equal to the volume. So the volume of this unit cell, if you wish, in the K space is exactly pi cubed over V. But I'm considering in this case the Fermi energy level, which is this entire surface in here that is made up to a certain point, because I have a certain number of charge carriers still, okay? In this case, electrons for a conductor. So that surface is given by this energy, which is h bar squared times k squared over 2m. The reason why I took it as sphere is because of simply I have this k squared, which is this number. So it's a sphere in this case of radius k. Okay, So what is the volume that I have in there? It's 4 pi over 3. This number cubed. But of course, I'm talking about at T equal to 0 Kelvin. So this will become my Fermi energy level. So this will become my Kf corresponding to EF. So that is the radius, the highest radius I can have for an N chargers. Having said that argument in here, but this is the entire sphere. I don't want the entire sphere. I want just the eighth of that sphere because of the fact that I only am taking the first octant. Since I take the first octant, I only need 1/8 of this number. I don't need the entire sphere. I don't need the volume of the sphere. I need just chunk of it where everything is positive. Because nx, ny, and z are 1, 2, 3, 4, 5, and so on and so forth. So kx, ky, kz are only these numbers. So it's only in the first octant. That's why I have to take the 1/8. But I also have, because of the Pauli exclusion principle, I can put 2 electrons in a given state. So I can put 2 of them in here, not just 1. And that is because I can have one spin up and one spin down. So this is how much volume of these cells I have, and each one of them comes up with this number. So I can pile up this many electrons. So that's basically what the ratio is telling me in this case. Okay, I have this many electrons that I can put in this volume in here, okay, where V is the physical volume. V is the length times width times height of that slab of material, basically, that I'm considering, that chunk of conductor that I'm looking at. So from here, obviously, I have Kf squared, and I mean Kf cubed, and Kf squared is related to to the energy through this expression. So in other words, I have the Fermi energy level in this point, which is equal to h bar squared times Kf squared divided by 2m. Get rid of this Kf. You have Kf squared and you have Kf cubed in here, and you have the energy. In terms of, this is actually at this point, we don't have charges. At this point, we have the number of states available. Okay. They have the number of states. I'm sorry. It's actually, since I used Kf, it's actually the number of the electrons because I started filling it up. In general, if I put the K in here and the K in here and E in here, any energy point in here, okay, in space, then in this case, I just consider, I'm counting the number of states available for my electrons. But when I start putting them, where I reach the maximum, that is actually the Fermi energy level. Okay, I hope that I made that distinction. Technically, I can put any energy surface I like, doesn't matter. That will correspond to a K that is given by this expression. That is the point. Then in that point, I can count my number of states as being equal to this number, which is, are the available energy states that I have for my system, period. Because I did not bring a single electron with me at this point. So the number of energy states that are available are the eighth of this volume times 2, because I have 2 states in there, one for spin up and one for spin down. So I technically have pi over 3 times k cubed, divided by this unit volume, because each and every one of them can occupy this volume. So this is my number of states. So this expression is true no matter what. And that's how we derived actually the density of states, G sub E, as being the ratio at which, in other words, how the states are piling up. In other words, look at it this way. Let's say, for example, I have my energy states there for this much energy. I don't know. Let's say, for example, E1. I have 2 available states, for example. For my E2, I have 1, 2, 3, 4, 5 energy states. And for E3, for example, I have 1, 2, 3, 4, 5, 6, 7, 8 states. Okay. For my E5, E4, I have, let's say, for example, 4, and so on and so forth. So I needed a function to tell me how much energy states are available for a given energy. This is the function that we're talking about. So when I start putting my electrons really in here, so in here I have 2 states. Remember, when I say a state in this point, that's it. It's done for. I can only put 1 electron there because I already counted the spin. So I can put 1 electron in here. I should put a minus sign. That's okay. E in here. I can put another 1 in here. This is the lowest energy. Then as I start to pile up, then I can put the next 1 in here, the next 1 in here, the next 1 in here, and the next 1 in here, and so on and so forth. Let's say, for example, this is my Fermi energy level. So at that point, I have counted all of my electrons. But this function is a regardless. This is true all the time. So it's giving me the density of states in here, which is how many states I have available for my electrons, for my charges, that I can pile up per unit energy. That's what this function is. So that's how we got that. But for the Fermi energy level, it's a specific level. At that point, you have a given number of charges. You have n of them. Okay, and the expression at the end of the day will be dependent on n over v, which is the density of charge carriers. Okay, so I hope, does this clarify somewhat the discussion that we had last time?
Yeah, a little bit.
Okay, so basically, there is a distinction here. Once you find the energy level in this point in here, because this expression, once you get rid of kf, I mean, you can solve for kf in terms of ef in here, and you plug it into this expression, you'll find an expression for ef in terms of n in this case, because from this expression in here, let's get, did we write it somewhere in here? Yeah, the 2 and the 4 and the 8 will cancel. So I can find now the n charges. So now I'm dealing with the Fermi energy level. At that point, it's going to be pi over 3 times kf cubed. Don't forget that you have v over pi cubed from the denominator, which cancels this pi. So the expression in here can give me kf equals to, what is it? 3 times pi squared to the power 1/3 times n over v to the power 1/3. What I did was take the cubic root of everything in here. Now I can plug it into that expression, and that expression will give me the Fermi energy level actually as being equal to h bar cube squared divided by 2m times this number to the power 2, because this is squared. So it's going to be 3 pi squared, I mean to the power 2/3, and then times n over v to the power 2/3. Okay, what is n over v? That is the number of charge carriers. And it is equal to the number of atoms, 1 or 2, depending on the valence of that atom. Okay, if I look at the periodic table in here, I'm looking at, for example, sodium. Sodium has 1 valence electron that can participate in the bonding. Okay, so in that case, it's just the number of the atoms. So it can, depending on the mass that I take from the atom, from the how much sodium I take, then I just have 1 charge carriers per unit volume in that case. But depending on how many atoms I have in this case, so that's going to be n over v. It's just the density really of the material itself, if you wish. Okay, but that's the density in the number, not the density in kilogram per cubic meter. For the case of magnesium, I have 2. So in this case, I have to multiply it by 2. So it's really Avogadro's number times 1 or 2, or depending on the conductor that we're talking about. So this number is basically because, and also, and that brings me to another discussion that we had, is how well do you pack them? That's actually where the density is coming. That's why we talked about the crystalline structure, and we talked only about 3 or 4 crystalline structures, but that also will impact the value of n over v. Okay, so that's basically in a nutshell. Everything else is just numbers in here. Each bar is just 10 to the negative 34 squared. M is 10 to the negative 31. And then these are just numbers. But this is the critical piece for the Fermi energy level. Make sense?
Yes.
Okay. Everybody else also awake, or only one of you guys is?
Yeah.
Okay, very good. Thank you. So this is just a follow-up on last week. And let me continue the discussion, because now once we have a different structure, once we have the bands are no longer overlapping, we have an insulator really. But that insulator can be, if the gap is not that big, like for the case of semiconductors, then we can have an interesting discussion to talk about. Otherwise, if the gap is big, of the order of 5 electron volts or higher, you don't have enough energy to really get much electrons going. So basically, when you pack the material together, at that point it becomes an insulator. So nothing is going to go anywhere, okay? So in that case, we don't really have anything going. So that gap between where the electrons are filled, so this is called the valence band, and where they could potentially, because these are energy available for it to go, and if it gets there, then in that case it's going to move. Okay, so that's the point being for an insulator in general. But this gap is too big, and when we computed it, the energy level associated with KBT, when we calculated it last time, it's really taken, usually it's about 25 or 26 milli-electron volt. So this is a tiny number, okay? And it's not enough to overcome this 5, for example, for diamond of 5.4 or 5.7 for 7 electron volts. This is too big. This is a huge, so it's not enough for it. Yes, few electrons, even at room temperature, because that distribution, Maxwell distribution, for example, extends all the way to infinity. So you will have some of them that will gain enough energy to overcome. So you will have probably 1 electron or 2 or something in a huge number. It's not going to be enough to do any kind of conductivity, okay? However, if you apply an extremely high voltage, that extremely high voltage will be enough to move the electrons in there, and that is the lightning, or that is the breakage, if you wish, of the dielectric that you saw also in physics 2. So at that point, the material becomes conducts like the lightning in that case in the air, which is an insulator. Okay, the typical calculations in here, because you can use the intraatomic distance between two atoms, which is of the order of a nanometer, by the way. Okay, and this is of the order of an electron volt. 5 electron volts is, I'm just getting the order of magnitude. So if you bring 1 electron in 1 volt over that distance, so what you need is 1 volt per that distance, which is 10 to the negative 9 or 10 to the negative 10 meters. That's what a nanometer stands for. So that is the electric field that you need. It's about 1 billion volts per meter. That could cause lightning, but this is really a theoretical number. Usually, in the case of the air, you don't really need that. You need just a few million volts per meter to cause lightning, because of the fact that you have actually some ionized materials in the air, and you have some impurities in the air that actually brings this number down. So you really don't need that for the voltage to cause that gap to be breached, and then you have lightning. But it's still a big number, even for the case of lightning. You still have a lot of clouds to build up to cause that discharge, okay? So this is for the case of big insulators. Other than that, these are useless. I mean, they're actually useful in terms of insulating. Otherwise, if you have a wire that is not insulated and you connect it, then you can get electrocuted. So you really need insulation for applications. So they're useful in terms of when we don't want electricity to flow or heat to flow. So that's actually important too from that perspective. Now, in terms of the semiconductors, the story is a little bit more interesting than the insulators. The gap is small. It's of the order of 1 electron volt, actually, slightly less for one material than the other. And nowadays we use silicon mainly. I mean, not mainly, I mean, for the most part, we use silicon more than germanium. So for the case of an insulator, for a case of a semiconductor like silicon in this case, the gap is still too big. 1 electron volt is too big. So the Fermi level, in this case, is taken right in the middle, and this is called the intrinsic Fermi level at this point. So the electrons in here, for the most part, occupy the states that are in the valence band. So this is still EV, and this is still the conduction band. But because the gap is smaller, you will have more of them, actually, than in the case of an insulator in the conduction band. So you'll have few electrons actually on their own, making it in here just with thermal agitations. And this behavior is different than the case of conductors. This is truly increases with temperature. In other words, the conductivity increases with temperature. It's not the other way around. So this is opposite for the case of conductors. In here, with the higher temperatures, you will have more electrons available to conduct electricity. However, so this is one type of conduction, is electrons in the conduction band. Okay, so they will conduct. In other words, if you apply an electric field by itself, let's say in this direction, for example, E, then in this case, this electron is negatively charged, so it's going to be subject to the Coulomb force EE, and that is going to be pointing in the opposite direction than the electric field, so it's going to move in this way. So that will get electricity, but not much really for a silicon pure by itself. So it's still behaving for the most part as an insulator really, but it's a lot better than a normal insulator, okay? So that is one thing. The other thing also, when this electron, the material is still neutral. In other words, if you take a piece of sand, it's still neutral, okay? So it doesn't have somehow negative charges floating somewhere. No, it's still neutral. So in other words, what happened in this case, there is a vacancy in here that was left when this electron moved up, and another vacancy in here, and another vacancy in here, and another vacancy in here. So each electron that migrates to the conduction band will leave behind a vacancy in the valence band. So this is a vacancy. And that vacancy can be occupied by the nearby electrons. So when you apply an electric field this way, this electron that was somehow sitting in here, and it's near its a silicon atom, and it was neutral, can actually jump to the next atom and fill that vacancy, fill that gap. Then it's going to leave behind it a vacancy when it does that. But then the next atom will do that, and the next electron will hop from its own atom when it's bound to the silicon atom and find an available next door vacancy and move on to it because of the effects of the electric field. So what's going on in this case is the electrons are moving in this way as if this vacancy, which is called a hole, by the way, is moving in the opposite direction. So here is the question: why in the world do I talk about the hole moving in this direction and not just keep tab of the electrons? Since I'm talking about the electrons in here, and just talk about electrons all the time. The electrons in the conduction band, well, we understand where they came from, and in this case, the valence band, I'll have to find the electrons that are bound to my silicon atoms, and then keep tab of them. And that is not a smart way of doing business. It's better to talk about holes, and I will explain why. Let's look at the structure itself. So somehow in here, I have a silicon atom, and another silicon atom, and another silicon atom, and another silicon atom. And let's just draw a few of them. I need a little bit more to see what's going on and why it's smarter to talk. Well, if you look at the periodic table, silicon is in the fourth group, okay, meaning that I have 4 electrons available for my bonding, okay? So in this case, I have this electron, one of each of these atoms provide an electron for this bond, and the same thing is true in here. So I have a double bond in here, double bond in here, same thing in here. And so on and so forth, okay? Here is the story though. One of these electrons has migrated already to, it's not there. It has migrated now, and it's available to float everywhere in the material. So it has gained enough energy, now it's in the conduction band. So in this case, I have a hole in here. So when I apply an electric field, another electron. Let's see, still apply the electric field in the same direction as we applied it earlier. This direction. So this is my electric field. So this electron can jump and fill this one, this gap. That's true. And if this jumps in here and fill it, then this becomes a complete and my vacancy moves on in here. But then I have another electron in here that could somehow jump in here. So this has jumped in here. So this is no longer broken. It's complete now. So this one will move in here and fill that gap, and that one, the one that is going to be empty. But which one really did move? That's the question. Did really this one move in here, or was it this one? Or was it this one jumped already here? Or did this one come into play? So that's why it's difficult to keep track of the actual electrons, and it's better to actually see where this thing is hopping. Okay, so it's better to keep track of this hole, this vacancy, and where it is moving. That's number one. The analogy, the textbook analogy that you will find in every textbook is with the bubble. Okay. Imagine that there is a bubble that forms, okay, inside the surface of the water. You guys watched any of those mafia movies? The guy who takes money from the mafia or whatever that is and doesn't return it. They tie something to his legs and they dump him in the ocean. So at this point, he's down in here and he's breathing the last breaths that he has or she has. And at the end, bubbles will rise to the surface. Okay? Don't try this experiment at home, please. Okay? So the point being in here, the bubbles will rise to the surface. Okay, you will go. So here is the deal, Natasha. When you don't befriend a lot of these people, okay, who do this thing in there, but try to find if they're going to do something, and you go and study this phenomenon, okay, and you report to us. How is that? Okay. 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 So the point being in here is, here is the problem. The bubbles that form are actually empty space, okay, under the surface. So they are equivalent to the holes that I'm talking about in here. But you know, and I know what's going on in this case is the water molecules are pressing on this bubble that formed underneath. And they're trying to fill the gap that has formed in there. Okay, so that's all what's going on in this case. So it would be crazy to go and try to keep which molecule came in and try to fill that gap, because that's the pressure really, and the buoyancy is difference between the upper pressure and the lower pressure to make it go up and up and up and up. Okay. No. Let's go and find one of those movies and see if we can understand it just by replaying the movie. Okay. Okay. Anyway, the point being in here is I mean, it will be nuts, crazy to actually try to track all of the molecules in here and see which one actually is coming to replace this bubble that has formed. So the same analogy in this case, it's much easier to actually keep track of the bubble itself and how fast it's moving, depending on the temperature, if you wish, depending on the gradient in temperature, how high it is. If you want to, this is the equivalent to the voltage or the electric field if you want to. And you can study the physics of it if you want to and report to the people, this is what I have learned about the bubbles. And depending on their size, depending on all of the physics that is involved, some of the bubbles actually, they can merge, they can collapse, and all of the other things that are interesting with them, for them. But the point being in here is, we would not actually consider studying the different molecules and how they move, trying to replace that gap. That's the point I'm trying to make in here. So the point being in here is it's easier to keep track of these holes that apparently have the same mass as that of the electron, and the same electric charge as the electron, except that their electric charge is a positive E, not a negative E. That's the only difference. Okay? That's the only difference between the two. Makes sense why we really have to talk about holes now instead of talking about hopping electrons?
Yep.
In the valence, very good, in the valence band. So basically the conduction is happening with two agents, two charge carriers independently, okay? Because these things can move. They don't necessarily, they are not associated with the one that they broke from them, okay? Two charge carriers, namely negative charges in the conduction band and positive charges, these are electrons. And positive charges in the valence band. And these are called holes. Okay, for all practical purposes, we're going to use the same mass. Granted, we will see the doping, and doping will give you some effective masses that are probably not exactly equal to each other. Even that of the electrons is not that of the exact electron, okay? Depending on the interactions, actually. Anyway, so this is typical semiconductor, okay? The gap in here, as I was saying, it's of the order of 1 electron volt, but really what they need is just half of that to overcome, to basically be above the Fermi energy level, okay? So that's the point that I'm trying to argue in here. And the next material of interest to us is actually the still semiconductors, but now we need to understand doping, because with doping, with a little bit of impurities, we can improve the situation drastically, okay? That's really what the importance of the semiconductors are. So imagine with me for a second that we take silicon again, but instead of putting another silicon in between them, we're going to look at the group 5 elements in here. And I have phosphorus, arsenic, antimony, bismuth, any one of those materials. Typically it's arsenic, okay? And I'm going to put it in there. So arsenic has 5, it's a group 5 in the periodic table, so it has 5 valence electrons. So 4 of which can bind normally with the silicon atoms, but it has an electron now floating outside. So it has available electron in here, okay? And this electron is actually very loosely connected to the arsenic nucleus. Why? Because of the fact that there is a lot of screening, first of all, from its own inner shells, okay? The Z number for the arsenic is 33. So there is 33 protons inside the atom itself. Yeah, it's 33 protons inside the nucleus itself. And there are 32 electrons that are shielding those 33 protons and basically making you look like as if you only have 1 electron, 1 proton binding to 1 electron, number 1, okay? Number 2, the distance is far away for that electron. So that is the inner shells, first of all. They are hiding, if you wish, if you want to, you can apply Gauss's law. And Gauss's law says that you have inside 33 protons, which are positively charged. Okay, but also you have 32 electrons that are negatively charged. So at the end, you will have effectively just 1 positive charge. That's what the electron would see, number 1. Number 2, the introduction of this additional electrons from the silicon, from the other silicon, will add to that shielding. So this becomes very, very loosely connected to the arsenic atom and brings its actually energy. If you do the calculation, it's going to be about 0.85 electron volt. This is if it was really a hydrogen atom, because I'm treating it as a hydrogen atom. All we have to do in this case is just use 13.6 divided by the n squared, and in this case, n should be about 4 or something like that. Anyway, the point being in here is this is how much energy. But then with the shielding effects, this number drops to about 0.01 electron volts. And this is plenty of energy to be overcome with room temperature. So in other words, this electron is free to move. It can be anywhere it wants to. So it's actually in the conduction band. So the presence of the arsenic in this material will take the Fermi energy level, which is the intrinsic one that was in here, and move it very close by about 0.01 electron volt from the conduction band. Whereas this is your valence band. So in this case, you will have a lot of, depending on the concentration of the arsenic, of course, you will have a lot of, because each one of them brings you exactly 1 electron. So the number of available electrons for the most part is going to be equal to the concentration of the arsenic inside your silicon lattice. Okay, so that is basically how you can form. In this case, the arsenic has given an electron, so it's called the donor. And the net effect in here, you have the conduction is really mainly with an N type. But don't forget that you still have those intrinsic electrons that has migrated in here by the normal fact that you still have your semiconductor. So you still have your holes in here, but they are far in between. So you still have a p-type also conduction, but it's very insignificant compared to the n-type in this case. So it's really mainly an n-type conductor. So the situation is usually not that straightforward, really, and when you do the calculations, because of the fact that you still have the process with which that generated those electrons in the first place still exist. In the normal semiconductor, you still have few electrons that migrate to the conduction band, leaving behind them holes, and those holes also participate in the conductivity. So in other words, the semiconductor's conductivity, which was poor to begin with, has been enhanced, but not replaced. So you still have that capability of the semiconductor also to do its own business, albeit now it's drastically improved by the fact that you have introduced impurities, because that's what this thing doping is. And that those impurities have given rise to more electrons in the conduction band that do the business, okay, of conducting. So this is one type of doping. This is called an N-type doping. Okay, another type of doping, which is the P-type of doping, is a similar fashion. You take your lattice in this case. So you still have your silicon in this case. But instead of introducing a donor, you introduce an acceptor. Acceptors are actually from the group that is the third group, okay? You have aluminum, you have gallium, which is typically used in this case, indium also, but depending on the availability, most of the time it's gallium. So those are of the third group. So the third group in this case, let's say, for example, Ga, have 3 electrons to participate in the bonding, but they're missing 1. So gallium, for all practical purposes, now is like silicon in terms of energy level. So there is an energy level available there, but it's not filled. So this is similar to a hole that has formed. Okay. So what it does in this case is going to grab an electron from one of these bonds and connect to it. Now you really have a hole in this case that has formed, because the gallium is bigger in size, physically size, than the silicon, because it has less atomic number. Actually, as a matter of fact, the Z number in this case is 31. So it has 31. So it's bigger in size, so it's going to impact more than versus the case of the arsenic, which is smaller in size actually, but it has already given its electron. In this case, it has taken. So this is actually called an acceptor. Okay. Note, and it's very important, that the net charge in this case is still 0. Because of the fact that, yes, you introduced an arsenic, and arsenic has given an electron, but it already has an extra proton, so it's going to cancel anyway. So the net charge is 0. So is here too. So the net charge is still 0. In other words, the fact that this gallium grabbed an electron in here, well, yes, itself is going to be ionized, it's going to be negatively charged, but that's fine. There is in here a positively charged because it lost its electron in there. That's the thing. So at the end, it's a net charge that's 0. In other words, when you take a semiconductor, it's still neutral. Okay. Doesn't matter which type of doping in this case. So in this case, it's going to be a p-type doping. So what's going on in this situation is it's the opposite than the first one. So the Fermi level is still, the intrinsic Fermi level is still in the middle. This is your valence band. This is your conduction band. And in similar fashion in this case also, once it grabbed it, it has moved actually the Fermi energy level by only few micro electron volts. And these are easily overcome by thermal agitation. In other words, what's going on in this case is that immediately with a slight increase of temperature, at room temperature at least, a lot of these electrons that were in here will find themselves have moved here. And they're bound now to the gallium atom. They cannot move. So what's going on in this case, the vacancy that was left in here, the vacancies, and a lot of vacancies have been left in here because of this migration of these electrons. And these vacancies are positively charged. All of them are. Okay. So all of them now are positively charged because the silicon in here has 32 and it lost one of its electrons. So it's going to be 32 and the other one is 31. So you'll have a net charge of +1 in this case. So what's going on in this case? So if I still apply my electric field, don't forget that you still have your intrinsic also n-type inductors from the fact that you're still dealing with silicon that has far in between electrons in the conduction band that will also do a conductivity. And also those ones, when they migrated, they left their own holes in there. Okay. So that pair that has formed through the generation process for a normal semiconductor still exists. But in here, the conductivity is predominantly by holes, dominated by holes. Dominated. Okay. So they're the ones who are going to be responsible for the conductivity of this material more than the electrons, which still exist because of the intrinsic process. Okay. So that is the point being in here. So in addition to the intrinsic holes that exist because it's semiconductor, the dopant now, depending on its concentration also, because for the main part, this concentration of holes is going to be exactly equal to that of the concentration of the dopant. So at the end of the day, you will end up with a high concentration of holes, and those holes can move freely now when you apply an electric field, similar to the bubbles as they form on the surface, okay? As they form underneath the water, I'm sorry, not on the surface of the water. Okay. Makes sense, this business of doping and things like that. So this is a p-type doping. P stands for positive.
Yes.
Okay. Which brings us to some devices that are used now in semiconductors, because semiconductors have tremendous use. They were discovered in the the end of the 1940s, and ever since they never looked back. All of our electronics now depends on them. Everything depends on them. Okay, so the simplest device, of course, is the photocell. So what the photocell does is that you have semiconductor in here, sitting minding its own business. And there are voltage, usually that voltage is variable voltage, okay? And you have a galvanometer in this case, okay? meaning it's very sensitive to small currents. So under normal circumstances, as I was saying, the conductivity is extremely low for a semiconductor or its own pure semiconductor. So this is what's going on. Unless you shine a radiation, in this case, whether gamma rays, which is pure energy, a pure electromagnetic radiation, or any other kind of particles in here. And if they have high enough energy that is equal to their HF frequency, where F is their frequency, is at least equal to the gap, to that gap of the semiconductor, about 1 electron volt. So in this case, the electrons will move, and because I have an applied electric field, so I see a higher current. So that is going to show immediately as a signal for that I have detected radiation in here of some sort. This is used extremely a lot in physics, at least in nuclear physics and in elementary particle physics, as particle detectors. So the minute that you see a signal, that means, hey, now you have digital counters. You don't really have a galvanometer, so it tells you how many of those came through. Okay, so it's controlled by computers nowadays, but it's really an important application for this whole thing. So this is one of its applications. Another application, of course, is the field of integrated circuits in general. And integrated circuits, they started initially with small ones. Then they moved to the small, or what is it, the large integrated circuits. You have so many of them, and the extremely very large integrated, so you have a huge capacity of them. In other words, if you were to open your cell phone and see how many of them in that basically CPU, you're really going to be amazed by them, okay? So let's talk about the simplest one of them, which is a diode. So the diode is a P and N type materials put together. Although that's not how the process works. The process, you make them actually together. You don't glue them together, because if you glue them together, there is a surface problem that increases increase the resistance, and it's going to really throw the whole thing out of whack. It's not going to work. Okay. So this is a diode. So you have a P type on one side, and you have an N type on the other. So this is called a PN junction. So the minute it forms by itself, remember, on this case, I have an excess of holes. And in this case, I have an excess of electrons. Not excess, I'm sorry, I don't mean excess. I mean holes that are free to move. So it's neutral. The charge is still neutral for both of them. And on the other side, I have electrons that are free to roam. And during the surface where they meet, the contact in there, of course, they will move. So the positive charge will move this way and recombine with the negative charge, neutralize basically themselves. And the negative charges will move this way and find holes to fill. So in this case, the whole thing is neutralized. But that can only go so much. Okay. So this is called this thing is called a diffusion, similar to what happened for a gas, for example, when it's in a large room concentrated, and you open to a lower concentration, so it's going to diffuse to the other side. That's exactly what you have in here. You have a large concentration of electrical charges in here and large charges in there, so they will move to do that. Okay. If a hole moves to this way, it's going to leave a negative charge on this side. If an electron moves from here to recombines from the other side, it's going to leave a positive charge on this side. And similarly, so there is an accumulation of charges actually in this junction, and that accumulation of charges will create its own electric field. That electric field, of course, will point in this direction from positive to negative. So this is the intrinsic one. I didn't connect anything. I just basically put them together. Okay, so there is an electric field now that points from positive to negative. Since it's pointing from positive to negative, it's really going to prevent further electrons from moving toward this direction, because remember, the electrons are going to be subject to negative EE. So if the electric field is pointing this way, the electrons will not be able to migrate in that direction anymore. So the buildup of that electric field will be strong enough to basically prohibit any further migration of the electrons in those directions. In the same token, the holes are subject to the force EE. So if the electric field is pointing this way, the holes actually will be encouraged to move in the opposite direction by this electric field that has formed. So what's going on really? I have two currents in here. Okay, two things going on in this. For each and every one of them, let's talk about the electrons first. Okay, the currents for the electrons, for the negatively charged particles, which are negatively charged carriers, which are electrons really. Okay, so what's going on in this situation is there is a diffusion current that is trying to increase this electric field. But then there is actually, because now you still have temperature and you have available electrons, so the process that generated those electrons to begin with, remember, they are in here. So now this one left, and another one came in to neutralize it. So proton came, a hole came in and neutralized this one. So the generation process takes over. So in other words, the diffusion is the one that caused this one to go, and this one to neutralize. But then now you have an arsenic atom that is neutral, and under thermal agitations by itself is going to create that pair again. It's going to create this electron again, moves it up in here. So you have a current that is generating them, which is this one, Ig, Ng for the negatively charged, and you have one that is taking them away, I of Ng, I of N diffusion, if you wish, recombination, because that's what the current is doing. It's recombining those electrons with the holes. So this is called the recombination current. So these two currents, when you reach equilibrium, thermal equilibrium will be equal. So the recombination current, this is the one that is coming from the diffusion. The diffusion is trying to recombine those charges, and this is generation. It's because of the presence of the impurities, period, at thermal temperature. So the two, when you reach equilibrium, will be identical, okay? The current, the electric field that is established is the one that is ensuring that is the case. And the same thing is true for my holes also. There is a generation current. I'm looking at it from the other side now. So there is a, the Fermi energy level is sitting in here, and as the holes are actually leaving, so now, and another one is recombining in here. So all of a sudden now I have a charge in here that can be actually it's the opposite direction. So the electrons will move in the opposite direction so that a hole is created in here. In other words, this is also true for my for the holes. In general, the two currents are actually equal, and I have reached thermal equilibrium. The explanation for it is this electric field that has formed. Okay. This picture in here needs to be fixed. Let me explain what I mean by that. When I reach thermal equilibrium, the Fermi energy level for my entire junction is the same. So this is where my Fermi energy level in here. For the inside, the valence band is closed from the Fermi energy level. So this, I'm sorry, the conduction band is closed from my Fermi energy level. So this is the inside. And this is my valence band, okay? For the case of the p side, so this is the p side, the valence band is close from my Fermi energy level, and the conduction band is far away. So this is how the junction look like. There is actually a nice theoretical explanation for why this curve should be like this, okay? But the point being in here, this is a thermal equilibrium. Now this is basically, when I have reached my equilibrium, that's where my Fermi energy level is sitting between the two, okay? So I have electrons that are trying to climb the field that has formed in here. And I have holes that are trying to climb this field also, because they are not supposed to go in that direction because of the electric field pointing this way too, okay? So both of them are in opposite directions, and that is basically what's going on at equilibrium. Here is when this thing is not in equilibrium though, when I don't want this to be in equilibrium. So now I'm going to connect it to a battery actually. So this is what I can do now to see if I can run current around this PN junction. So again, this is my PN junction. So this is really where the band has formed, okay? So this is my N type, this is my P type, and now I'm going to connect it to a voltage in this case, and simply as that, okay? I can put a galvanometer if you want to, but this is my voltage now, okay? So this is my voltage now. So what this voltage is trying to do is trying to encourage, because it's pushing more positive charges in this way and we're putting more electrons in this way. So what it's trying to do, it's going to try to encourage the recombination on the expense of the generation in this case. The generation is still due to thermal agitation still, okay? But the recombination now is enhanced by this external voltage. So the presence of the voltage now will be pushing more and more electrons in here. And the analysis is actually coming from thermodynamics using something called the Gibbs free energy. And we used it to some extent without calling it that. So basically what's going on in here? The fact that each electron now is subject to an electrical voltage difference, delta V, if you wish, this is delta V, is equal to, the energy in this case is going to be equal to, let's write it as energy. Instead of V, we usually write it U, okay? So the potential energy in this case is going to be minus E times this voltage that I have applied, okay, for the battery. So each electron will be subject to that one. But at a given temperature, the new recombination basically rate is going to be proportional to this factor, and the factor is given by exponential of minus delta U divided by KBT. In other words, this is the increase in recombination, increase in recombination over the because of this enhanced energy that was given to them over the equilibrium values. Equilibrium value. In other words, the current now is going to be given with the old current, which is this one. Actually, I should have probably given it a label of 0 or something in here. This is at equilibrium. So I'm going to give them an index of 0 or a superscript of 0, not to the power 0. That's basically equilibrium. At the end, we're going to just give a different symbol for them. So the actual recombination now for the charges is going to be the old one, which is taking them in absolute value because at the end I'm going to add them up. The old one times this exponential factor of this negative delta U over KBT. But the negative times negative is going to be positive. So it's going to be EV over KBT. So this is the rate with which this electrons are going to be enhancedly moving this way and actually going this way. And also in the same fashion, I can do the same thing for my, this is the increase. Okay. And the same thing with my protons, positively charged electrons, positively charged holes, I'm sorry, times the same exponential factor divided by KBT, okay? So when I add up all of these numbers, this is going to be the difference, but there is still that generation process, okay? There is still that generation process that is in the opposite direction to this electric field to this basically external voltage. So at the end of the day, the sum of these two will give me the actual current, and is going to be the actual current, which is called the saturation value in here. The saturation value times this exponential of EV over KBT. And how much is that saturation value? It's exactly at equilibrium values, but that's in the opposite direction. So this is going to be IS exponential of EV over KBT minus 1. Okay, this is not honestly exact proof for it, because the proof for it requires a little bit more advanced tools, including thermodynamics. But this is a good enough explanation for the law that we will be using for the conductivity in this case. When we connect it this way, it's called a forward bias. If I take my battery and flip it and put the positive on the other side and negative on the other side, I'm going to basically hit a wall. I'm going to hit the saturation in this case. So it's going to be in the reverse bias. This expression is valid for both V positive and V negative, actually. And if you plot this function as a function of voltage, the current, so we're going to take both positive and negative. So this is the voltage, this is the current I. So this is going to be forward and negative, and forward and in reverse bias. When V is equal to 0, this expression is 1 minus 1, which is 0. So it passes by the origin. That's good, actually, because we want it when there is no electric field, that we don't want the, that's the equilibrium, back to equilibrium, basically, where the two cancel. Okay. So at the end, this expression is going to go exponential for large values of V. So this becomes irrelevant. And for low values of V, this exponential would drag to 0. So for V, that is negative, large negatives. So this is going to be 0, and the value of the current will just reach the saturation value, IS, in the negative direction. Okay, negative IS. And then here is the voltage in there. Now, provided you don't apply huge voltage in the opposite direction, because if you apply huge voltage, this will break. Okay. You reach the breakage point in here. This voltage in here is very small, is of the order of 0.6 electron volts. Volts. It's a voltage. Okay. So this current is this voltage is very, very small. Also, you reach extremely high currents. So you have to really be careful with the diode. You don't want to apply too much voltage on either direction. And it turns, because this IS is extremely small, typically in the applications, it's of the order of either a micro or even a nano ampere. So practically there is no current. You want it to be as small as possible. So this one will act as a switch to turn off the current if the current reverses, completely shut it down, and open it in the opposite direction. Okay, open it to whatever values. So this is basically what the role of this device is. It plays more of a role of a switch, really, that will allow current to be open in one direction. So this configuration is not advised. You really have to have a resistance in here, because this currents can be very high very quickly. So you want to tame them down. Okay, so so in this direction, it's going to allow all of the currents. It's really like an open circuit. Okay, I mean, not a closed circuit. It acts like a wire, really. And then, so all of the current is going to be tamed by this resistor in this case. Okay. And then in the opposite direction is going to be open circuit. So it's not going to allow any electric current to fly through. Okay. So it behaves more like a capacitor in that situation. So, but this is basically one of the applications of this device. Now, a word of caution. The big thing in here. In the case of Ohm's law that I wrote earlier today, actually, we have this relationship which is linear. Remember, I, in the case of Ohm's law, is equal to the voltage over R. And this is a line that has a slope of 1 over R. So this is Ohm's law. Okay. And this one starts small, but immediately grows very high. So it meets the Ohm's law in 2 points, 0 and in here. So both of these laws are not the same. So in this case, this is a non-ohmic device. Okay, this law is linear. This is not linear. This is actually a non-linear device also. As a matter of fact, all of the electronics that uses integrated circuits is non-linear. It's called non-linear electronics anyway. So as opposed to what you did so far in physics 2, which was all linear, you increase the current by 1 amp, for example, the voltage must have increased by 1 unit, okay? So that the ratio stays the same. In this case, no, it's not the same. These devices are not the same. Sometimes you increase it and nothing happened for the current and vice versa, okay? Or happened drastically that it's completely not in a linear fashion. So that's why these devices are called non-linear devices. Which brings me to a last point in here to talk about, and that is the transistors and the superconductivity, because we really want to finish this one. I was hoping actually to jump into another topic today. I know we have a break today, and we probably are going to do it because of the fact that we have, I thought it's Tuesday today. I'm sorry for a second. Okay, today is Thursday, so good. Okay, so we still have 2 topics to talk about in here. First of all, transistors. For transistors, it's actually, you have 2 types mainly. You have the PNP and NPN. So what I mean by that? In the case of a PNP transistor, you have an N material squeezed between 2 P doped materials, okay? And in the case of an NPN, it's the opposite, that's all. So you have a junction in here, and you have a junction in here. Same thing in here. Yeah, this is a PN junction, and this is an NP junction. And in this case, this is an NP junction, and this is a PN junction. Okay? Junctions in opposite directions. Both of them are, they have 2 junctions. That's why these devices are called bipolar junction transistors, or simply BJTs, okay? So if you hear this terminology used a lot, that means it's this type of one or the other, okay? In a circuit, by the way, the representation of a diode in a circuit, because of this configuration, this is how you represent a diode in a circuit, okay? So this is the P, this is the N, okay? And this is basically how you're represented in a circuit. Same thing in here for transistor, depending on what type, is going to have, this is called the base. This is called the base. One of them is called the collector, and the other one is the emitter. Same thing for the other one too, okay? So in this case, what do you have? You have, this is how transistor is represented. In electronics, okay? Now, the arrow pointing away this is an NPN junction, and the opposite is true when the arrow is pointing in. So this will be your emitter, this will be your collector, and this will be your base, okay? This voltage difference in here is a fixed value. That is your 0.6, 0.7 volts, okay? So this is really most of the applications for it, okay? So this value is fixed. In a typical transistor, what you're interested with is the voltage difference between this point and this point, and that is called the VCC, okay? And also you're interested in the gain in this case, which is called beta. So this is the gain of the transistor. Okay, transistors can be used for 2 purposes. Either to amplify a signal that is weak on this side, weak signal. So this is one of its uses, which is amplification of a signal, like your speakers. They amplify signal, okay? And also as a switch too, switches. And it's the latter part that is the main application, okay? This is what is used in logics. Either the current go through or not go through, really. So this is what is used in logic circuits. Okay, there are two types of transistors that we really don't cover in here. And the first one is a MOSFET, and the other one is a hybrid, okay? Those, they use a little bit different configurations. They're still using a PN junctions, but they actually don't have, I mean, they don't use junctions, I'm sorry. They still use P materials and N materials, but the junction is actually happening with something called the gate, where the current increases just enough for them to basically build that gap, okay? So they use a different technology, at least for the MOSFET. The other one is a hybrid, actually, between this one and the MOSFET, okay? So those are the types of conductors. I know in this college, we really don't have a more advanced class, so this is the extent with which we're going to cover this topic. Still have about 4 minutes before the time is over. So we need to talk about another type of materials. And those materials are superconductors. I know you talked about them when you did physics 2, when you talked about magnetism and the fact that they reject magnetic field and some peculiar properties that they can use them for levitation and things like that. But what is a superconductor? Superconductivity is a little bit different approach than a normal conductor or a semiconductor or an insulator, in the fact that it's happening with a different approach to altogether. All of this behavior up to this point is due to the electrons or even the holes, and both of them are acting as fermions, actually. In other words, they can't put two more in the same energy level. They have spin 1/2, okay? That's basically the whole point in that. This one, actually, superconductivity is actually being caused by bosons, okay? So it's a different approach. It's still by electrons, but the electrons pair together in such a way that the net spin is 0. So in this case, they are bosons, and their wave function is symmetric. So this is what's going on. When the temperature drops to very low temperature, extremely low temperatures, right? At this point, I think we are still within a few hundred Kelvin, so we still don't have room temperature superconductors, because the lattice itself, which is still made up of positively charged, basically, carriers, which is a normal conductor now. We're talking about a normal conductor. So they will be hardly moving at very low temperatures when T is very low. Okay, so they would be hardly moving. So what happened in this situation, if an electron passes by, it's going to drag them slowly, this positively charged ions. The material is still neutral. So this is an ion and this is an ion. They get closer. They get attracted to that electron as it's passing by. This creates a net positive charge. This one moving closer and that one moving closer. So there is a concentration of charge, a positive charge overall in one region of the lattice, okay? That is what is known as actually that excitation propagates in the entire medium at that point, albeit with the speed basically of sound in this case. So what's going on in this case, another electron discovers that there is an increase in charge in here, so it gets closer. It's attracted to this positive concentration. And now these two electrons form a pair that moves together. And that pair will continue moving and basically helped by this configuration with no collision whatsoever. So in other words, the resistance drops to 0 of the material. The material becomes superconductor, meaning it has no loss whatsoever due to Joule heating. The pair that forms in here is called the Cooper pair. And it was due to Mr. Bardeen, Cooper, and Schrieffer, who came up with this theory. Now the theory is called the BCS theory. And it explains beautifully how this material forms. So now the key thing in here, that this pair of charges, that is the one that is conducting, and that pair, as I was saying, is a bosons. They're not fermions, which means I can have all of them in the ground state. Okay, which is something I can do with fermions. Fermions, I can only have one fermion per energy level. I mean, when I count the spin, of course. If I don't count the spin, only two, one up and one down. But this one, they're bosons, which means I can have them all in the lowest energy possible, moving unimpeded. So I can have another pair forming in here. And another one in here. And these pairs, they form everywhere in the lattice in this case, and they move without collision. And they move with the lowest energy possible. And they have the same energy because they're bosons, their wave function are symmetrical. So meaning that they can all coexist. And it's the pair that is now the part, that is the one responsible for the conductivity, not a single electron by itself. The two together, working together, really, making that happen. So the resistance drops to zero and the material becomes conducting. So if I keep that temperature extremely low, the material, and start the current somewhere, I can have an infinite loop of current that can go forever and ever and ever and ever and ever. It never stops. There is no heating. There is no loss of energy whatsoever. Okay, and that brings some interesting applications. If this were to be applicable at room temperature, we would have materials that conduct electricity basically free of charge, and the electricity, the cost of it becomes so ridiculously cheap that it becomes like water, basically, or even cheaper than that. Okay, so it becomes so cheap that it's really ridiculous. So that's the point being in here for the this ones. Unfortunately, at this point, with a slight higher increase of temperatures, this bond breaks, the pair breaks, and when it breaks, we go back into this old behavior of fermions, and now they go all over the place. Okay, so we can do that for higher temperatures. So the energy that is for the formation of this Cooper pair is very low. That's why it requires low temperatures. Okay, make sense?
Yep.
Okay.
Yep.
Okay, very good. So when we meet, I'm going to do two things. First of all, we're going to talk about the lab, which is part of our requirement for today. And then we're going to talk also, introduce the topic, chapter 43. We're not going to do applications until we're done with all of the materials. Still have only two chapters, which still have 43 and then 44. And then we're going to sit down and do some applications that are relevant for exam 3. And that's it. So today we're going to meet in about 15 minutes and around 9:40. Would that make sense for everybody?
Yep.
Yep.
9:40.
Okay, so I'm gonna pause the recording and I'm gonna shut down my microphone and the video, but don't go, okay? We're still not done. Hi guys, and welcome back to the second part of today's basically class. So the first thing I really need to do with you guys is share with you the lab, so that we have the same same understanding for the lab. And then depending on how much time we have left, we're going to cover a little bit of some of the ideas for chapter 43. So let me first of all find the lab. Modules. This lab is not going to be hard too, okay? So as a matter of fact, you should, in terms of doing simulations, I don't think that there is a lot in it. There is a GeoGebra link in the instructions. So you need that link in the instructions, but why did not open it for me? Okay, never mind. I have it in here, so I'm going to use it in there. No problem. Share. The lab. Are you guys back?
Sadly,
Yep.
yes.
Okay, very good, very good. So basically, this is the lab. It really goes back to the Niels-Bohr's model, which is way back in chapter 38, if you guys remember. Okay, so this is stuff that we did a long time ago in terms of the model itself. The theory is not hard at all. The theory is that what we did, remember, Mr. Bohr assumed that somehow the wavelength of the orbit and the wavelength, they are connected via this relationship, basically. In other words, that there is only a given number of wavelength that cover the radius for it to be stable. That's his argument anyway. That is similar to the standing waves on a string. So if you have a 1 full wavelength or time and a half wavelength, anyway, you have to have nodes at the ends, basically, that tie back the electron in its path. And that's a condition for it. And that is a quantization for R, if you wish. And that leads immediately to the quantization of the angular momentum. So, and that led him to L equals to NH bar. And that's not actually wrong, because that's exactly what we found when we did quantum mechanics, except we don't use the symbol N in there. We use the symbol M for it. And M and L in this case actually has two values. The length of the angular momentum is square root of L times L plus 1 times H bar. And its projection along those directions are given by M H bar, where M can be any one of those numbers from positive L all the way to negative L. Okay. So that's basically this is the old model. This is the Niels-Bohr model. And if I use the expression for the force, then and equate, this is classical mechanics now, F equals to ma, really, that's all. This is the force, the electrostatic force, and this is the mass times the acceleration, because we're assuming that somehow the electron is going around the nucleus in a circle. Obviously, this whole model is not accurate, so that you guys know, in light of what we learn now, okay? So that actually leads, combining this equation with this equation, you solve for R in here. And you have a solution for R in here in terms of V. And you have two equations. You have this equation has two unknowns, V and R. And you have this equation also has V and R in it. Everything else is known. So from here, you can solve for these two equations and find these two equations for N, R, and V, okay? R is proportional to N squared, this quantum number that he introduced, and V is inversely proportional with N. So you can show this one, so it's not hard to do. And also, this quantity now is called A naught, so you need to evaluate it. And alpha, which is really the ratio of this velocity over the speed of light, is that fine structure constant that we found in there. And it's going to be relevant down the road, actually, for chapter 44, okay? So again, you're supposed to evaluate these numbers. Okay, this should be around 1 over 100 over 37, 1 over 137. Okay. Okay, then you're supposed to take this expression that you found from equation 1 to find the total energy, which is just the difference between the potential, the kinetic energy and the potential energy. And the kinetic energy is 1/2 times this mass of the electron times this velocity squared. We're using classical mechanics, pure and simple. Okay. And minus the potential energy, which is the electrostatic. So when you see Ke, it's 1 over 4 pi epsilon naught. That's all. Okay, it's the electrostatic constant in this case. It's 9 times 10 to the power 9. So you're going to sub in here, and it's going to be some fundamental unit divided by n squared. So you'll have an n squared in the denominator, and all of the other stuff is going to be in the numerator. Okay. And evaluate E naught. So if you do the calculation, you're careful with it, you're going to find 13.6 electron volt, because you are supposed to do it in electron volt, okay? So you're supposed to do this calculation. And then, of course, the difference between the energies is going to be the final state minus the initial state, and it's going to be, both of them are dependent on n, so it's going to be the n1 over n squared, because they are negative, so it's going to be given by that expression. Lambda is given by the de Broglie wavelength in this case, and there is a minus in there because typically this number could be positive or negative, depending on if it's absorption or emission. Okay, so what I mean by lambda in here is going to be always positive, of course, the value of lambda. But if delta E is negative, you place the negative in there. If delta E is positive, you place the positive in there, and you interpret that either as an absorption or emission. That's all. Okay. So if you jump from a higher energy level to a lower energy level, in this case, is going to be a negative energy, and the energy is going to be given, and the wavelength is going to be still positive. If you go from a low energy to a higher energy, that's going to be an absorption of a given wavelength lambda. Okay, so this is some of the information about the visible spectrum in this case. Okay, these are the red, green, and all the way to violet, where the ranges are. Okay. So on table 3, first of all, you need to do table 3. Okay, here is table 3. Before you do that, you need to do table 1. And before you do that, you need to do table 2. So table 1 is coming from this expression for En that you find, this one. Okay, and you're going to sub the values of n equals to 1, 2, 3, all the way to 6. So you're going to fill the gaps in here. E1, E2, E3, all the way to E6. Make sense how to do this table 1? Yes?
Yes.
Should I repeat it? Okay, very good.
Can you actually repeat it?
Okay, take this formula. This one, En equals to negative E naught over n squared, where E naught you're supposed to have computed it in here, in this question. And change the value of n, 1, 2, 3, 4, all the way to 6. And fill in here. Make sense, Natasha?
Yes. So I was writing it
Okay.
down and then I missed it.
Sorry, very good. No problem. And then table 2. Table 2 now, you're supposed to use this formula for lambdas, okay? You have to pay attention now. You have a delta E. Where is that delta E is coming from? This is your initial, this is your final. Obviously, you cannot have an initial that is final, okay? So if your initial is 2 and your final is 1, so from 2 to 1, so replace 2 for initial. Where is the expression? For the initial is 2, so this will be 2 squared, and the final is 1. So 1 over 2 squared minus 1 over 1 squared, and that is going to be delta E, and the number is going to be negative. So when you plug it into this expression, make sure you put it in maybe you need to put it, leave it in signs, okay? Leave it with the negative values in here, okay? So you calculate delta E's, that's all at this point. Changing the initial and the final, and the initial, some of them are going to be positive, some of them are going to be negative, okay? Actually, this we're going to be, negative, and this one is going to be, okay, the final is 2, and the initial is 1. So the final is 2, and the initial is 1. So if the initial is 1, and the final is 2, so this is going to be positive. This is going to be negative, and it's going to be the same value, okay? And the same thing for this one. Make sense on how to fill this table? It's delta E's, that's all.
Yep, seems pretty simple enough.
Okay. For lambda, just use the positive values. Don't worry about the negative ones, okay? So take either one of this, but you're taking it in absolute value, okay? And you're computing this number, this lambda. Again, you just computed delta E, and you have a bunch of constants in the numerator. Make sense?
Yep.
But the only thing that you have to be careful with, you computed delta E in electron volts, and each bar actually is given in electron volts second. Don't put 10 to the negative 34 in here and all of that stuff. You already have each bar in electron volts in this case. So you just divide that electron volt by electron volt, and you will have a meter per second in here. And there is a second in each bar that cancels that second and the speed in here of light. And at the end, the value will be in meters. You can actually make sure that it's in nanometers, because you would want to compare it to these numbers. Okay, so you're supposed to look in here now for question 3, actually, for table 3. Okay. And you're going to tell me which one is going to be in the visible range. Is it going to be in the visible range? It's going to be which colors you're looking at. That's the question really that deals in here. So you're supposed to look at the number that you find in here. and see if any one of them fits in this this ranges. And you're going to tell me which colors are. Make sense?
Yes.
Okay, so that question is easy enough. Now we're going to do the simulation, and the simulation is going to give you a value of L. We're going to give you the value of X1 and X2. And the value of X, and X is actually equal to this number, X2 minus X1 over 2, okay? And you're going to put it in here, and you're going to compute lambda using this expression in here. And these are the colors that you supposedly should have found, okay? A red, aqua, violet, and then violet, okay? If we did this in the actual lab, you will see these colors actually pop up, okay? But the simulation will just give you those numbers, and you're going to compare the theoretical values with the experimental values that you found in there, and you're going to find the percentage error, okay? And this is the correction due to the fact that we did not include the motion of the proton. We assume the proton is somehow fixed in the case of the hydrogen atom, but both of them are actually moving around the center of mass, so I should really use the reduced mass instead. So the expression will change slightly, and this is the correction with it, where mu is actually a reduced mass in this case. This is a reduced mass. So at the end of the day, you're supposed to find how much, this is how much errors are, okay? So questions 5 and 6 should be easy enough. If you guys have difficulty with them, please let me know, okay? So this is the entire lab. It's not really that hard. All you have to do is make sure you go back into, where is the lab in here? Make sure you do this simulation in this link and you're done. This is the report. Make sense, the lab?
Yes.
Yes.
Okay, it should be straightforward for the most part. Now, again, if you guys have any questions, please let me know. We still have one more lab, and I don't think that it's going to be hard. It's going to be more work than this, but it's not really hard to do also. Okay, let me introduce for you guys chapter 43, okay, as promised. And then we will finish it hopefully early next week. And then we will get into chapter 44 and hopefully finish it within the end of the week after. I'm hoping by the beginning of May, we would have finished everything, because we still have an exam on May 12th and actually the post-test, and we also have the final on May 19th. So I think we're going to be okay. I think we're going to be probably, we'll have 1 or 2 periods at the end of the day where we don't really need to meet, except to do applications. So that's basically where the whole thing is. Okay. So I took the liberty, let me share with you the screen actually. When we took the break, I wrote some numbers in here because I cannot remember them. And if you guys remember them, I would be very proud of you, because this is the atomic mass unit. Okay, and this is actually the mass of the proton, the mass of the neutron, and the mass of the electron. The only thing I can tell you is I remember the mass of the proton, 1.67 times 10 to the negative 27. I can tell you also the mass of the neutron, which is almost the same thing, 1.67 times 10 to the negative 27. But as you can clearly see, the mass of the neutron is slightly higher than that of the proton, and this will be relevant down the road, okay? This will be important. And the mass of the electron is easy to remember. It has 9.11 times 10 to the negative 31 kilogram. And all of it is related to the atomic mass unit. In chemistry, we use AMU, okay? And also it's used in physics too, but it's actually short of U for the atomic mass unit, okay? So this is basically the mass of a given unit in here, of how many of it it's going to be. So that's basically the number that we use. Actually, we use carbon 12 for that to define it. So these are some of the physical properties of the elementary particle. So we're doing chapter 43, by the way. So we're not studying now the atom anymore. We're just focused on the nucleus. And the nucleus, you can think of it as made up of a bunch of nucleons, okay, held together by nuclear forces, okay? So this is basically in a nutshell that what this is. So each one of these small circles is a nucleon, except they come in two flavors. So you have the positively charged ones, namely the protons, and you have the ones that don't have a charge, namely the neutrons. So this is basically in a nutshell how a nucleus would look like, at least a picture that we have in here. And a bunch of them, for a given atom, you typically have n neutrons, and you have Z, which is the same thing as the number of electrons for a neutral atom of protons. And again, as I was saying, the number of electrons is equal to the number of protons in a case of a neutral atom. Okay, and the atomic mass in this case is given by the sum of these two numbers, n plus z. Okay, so roughly the mass of the nucleus, if you wish, is this number n plus z times this atomic mass number. Okay, or if you wish, it's the mass of the entire molecule, the entire atom, because of the fact that the mass of the electrons are extremely negligible. As a matter of fact, the mass of the electron is that of the proton divided by 1,836, if you do the ratios for it. So it's almost 2,000 times lighter than the proton, or 2,000 times lighter than the neutron. So this is basically the smallest constituents. So what we're doing now, we're doing nuclear physics. We're going way beyond the atom, and we're going inside the nucleus. The distance from here to here, it's typically of the order of a femtometer. Remember, the nucleus is about the order of A naught, which is the Bohr's radius, which is about the order of 10 to the negative 10 angstrom, which is 10 to the negative 10 meters. And this one is of the order of 10 to the negative 15 meters. Okay, so this is the sizes that we're talking about, extremely small sizes. This is the size of the nucleus, typical size. That's a femtometer. A radius of the actual nucleus is given by this expression. It depends, of course. The more I jam in more nucleons, these are called nucleons, by the way, both of them are nucleons. The more I put in, the bigger the nucleus starts to grow. And it grows, as a matter of fact, as a factor of 1 to the power third of this number A, of the atomic mass A. So more I put in, the more this basically size of the nucleus starts to grow, where R naught is a typical number. Again, this is experimental data now, where R naught is 1.2 femtometer, or 1.2 times 10 to the negative 15 meters. Okay, so it grows. Yes, it grows. Okay, but how big is it relatively speaking? So if I take, for example, uranium-238, for uranium-238, in this case, A is equal to 238, actually. And if I want to compare it, for example, to iron, iron is what, 56? So in this case, A is equal to 56. So the ratio of the two sizes, if you wish, in terms of diameter, is going to be of the order of the ratio of this number over the other one, but the A is changed. So the R naught cancel the R naught, so the ratio, in other words, how big uranium atom is compared to compared to iron. So in that case, it's going to be really A for iron, which is 230 for uranium, which is 238 to the power 1/3, divided by 256 to the power 1/3. Just to give you an idea of the sizes, okay? because I want to find this number, and I did not pull my calculator quickly in here, so it's going to take a little bit to pop up. I want to find how big this number is, how big they are, relatively speaking. And you will see that they are not really that big in terms of size. So when I was saying earlier about the about arsenic and gallium, and the fact that one of them is bigger than the other, I meant the atom. I didn't mean, of course, the nuclei. Okay. So that's really what the whole point in here. And the atom has to do with something else, which is those big distances I was talking about. This is about 100,000 times bigger, the atom, than what we're talking about, this size in here. So let me share with you the screen again. Let me change the view format, environment, slideshow, and let me stop sharing and share calculator. So I really wanted to see this ratio, honestly, and it's I don't know the answer. So it's going to be the square root of 230 or to the power 1/3 divided by 56 to the power 1/3. And if I don't put a decimal point somewhere, it's going to give me probably a number that is some sort of a fractional representation or something. So it's about 1.6 times bigger. That's basically the whole point of this exercise. So it's not like this much big of uranium-238, which is the largest nuclear, the largest atom that basically occurs naturally, versus 56, which is iron, which is a common element in there in the middle of the periodic table. So this is not that big. 1.6 times bigger is not that big in terms of nucleus. So as you put more and more nucleons inside the nucleus, it grows, and it grows according to that cubic law with the more nucleons you put. But because of the cubic relationship, it doesn't really grow drastically, okay? The cubic law doesn't grow linearly, like, for example, when you increase. In other words, when you double A, it doesn't double in size. That's the whole point in here, okay? So it's really not that big in terms of that number, okay? So which brings me to an interesting point in here, okay? Since we mentioned the units in here and all of that, one of the ideas is trying to find the mass of these objects, the mass of the nucleus. Obviously, the more you put in, the more nucleons you put in, that means you're increasing A somehow, either adding more N's or adding more Z's, but both of them are almost the same mass, okay? Both of them are almost the same mass. So what's going on in this case, the density should stay the same. Let me see why that is. So the mass is proportional to A. Because again, if you double the nucleons, you double the mass, because each and every one of the nucleons that you bring them in will bring its own atomic mass unit, which is very close from 1. Okay, so it's going to increase with the number A. Okay, in other words, the mass will be exactly, or at least roughly, very close from A times U, where U is the atomic mass in this case. As we will see shortly that it's not going to be a little bit off, and we will see why. Okay, because you need some bonding energy to keep them together. Otherwise, what's the point of having to jam next to one another so many protons and neutrons, and at the end they don't glue? So as a matter of fact, the protons, they don't want to stay next to one another. They're positively charged. They want to repel one each other. So there is no reason for them to stay together. So there is some energy that is required to put them together, and that energy needs to come from somewhere. It comes from what we're going to call the mass defect right now, the difference in mass, and we'll see that it's very small. But the mass is very roughly closely equal to A times that unit mass, the atomic mass, the AMU, the atomic mass unit. The volume now, if it is a spherical shape, and I wrote it already as a spherical shape, should be 4 pi over 3 times the radius cubed. And this relationship immediately gives me 4/3 times pi times r naught cubed times A to the power 3 over 3, which is A. So the density of the nucleus, rho for the nucleus, it doesn't matter which, is going to be a constant number, more or less. is going to be U times A, that's the mass, divided by 4 pi over 3 times pi times R naught cubed times A, and A cancels the A, and that is actually how we got the result to begin with, honestly, okay? So it's an experimental observation that the density doesn't change from nucleus to nucleus to nucleus. Then that's how we arrived at the conclusion that the radius then must be proportional to the cubic root of A, because then if I cube it, it's exactly what is needed to cancel the A from the numerator so that the density doesn't change much from nucleus to nucleus to nucleus, okay? So this is basically some of the properties of the nuclei. So again, I was referring to that the mass defect. So I really need to define what that mass defect, because I really need to find the binding energy of a nucleus. And it's exactly that difference in mass. So the delta M, which is by definition the mass defect, efficiency, if you wish, is equal to the mass of the, if you look at table 43.2. Table 43.2 gives you the mass of certain elements. One of them is the hydrogen molecule, the hydrogen atom, I'm sorry. This is the hydrogen atom. So if I take the number of protons, Z, and multiply it by the mass of the hydrogen atom, this is the hydrogen atom itself, okay? That means I already counted the protons and I counted the electrons in my basically atom that I'm considering in this case, okay? And add to it, and this is coming from that table 43.2. In other words, that number should be, what is it, 1.007825. So this number is actually 1.007825 U, where U is given up there, okay? Plus the number of protons, the number of neutrons, I'm sorry, times the mass of the neutron. And the mass of the neutron is given, did I give? Yeah, I think we did. This mass, okay? So if I add up these two numbers, this gives me the theoretical value of how much the mass should be. But I have an experimental value that I need to subtract from it, and that is the mass of that atom. So that is an object in here, not A, that has that number Z with that atomic mass A. So, and again, where do I get that value? I get it from the same table, 43.2. If I do this math, I will find that the difference is not exactly zero. In other words, this mass is slightly less than the sum of these constituents. So in other words, in order to make this atom of this element of a given Z and a given A, what I'm saying in here is gather Z protons, okay, and Z electrons. So basically you have formed now a hydrogen Z times hydrogen atoms. That's what you did. And then add to them N neutrons, collect them together, and now you have made that atom basically that we're talking about, that element. But if you look at the actual the mass of this one, if you, for example, do experiments in chemistry and find its atomic mass, find its molar mass and divide by Avogadro's number and do all of your stuff, you will find that that mass is slightly less than this numbers, and that is what the mass defect is. Which brings me to another idea then, that the binding energy EB is equal to that deficiency in mass times C squared. So it seems like the way that we're fusing those things together is that by losing some of that mass and making the nucleus the way it is. Because the electrons, they're sitting in the cloud, they're not really participating in this. That's why I have to use the hydrogen atom in this case, because I have Z of them, and I also have Z of them in here, so they cancel out, okay? So I'm not worried about them. So this is actually the nucleus, so the mass of the nucleus, the difference in the mass of the nucleus. So all of this binding is coming from the mass of the nucleus. So this is my binding energy. Okay. Word about the units. Okay. C squared is equal to 3 times 10 to the power 8 squared. And that is 9 times 10 to the power 16 10 to the power 16 meter squared per second squared. Okay. One way of converting this to an energy is to basically saying how much U in here. So I'm going to multiply it by U and divide by U in here. And I'm just going to be dealing with those coefficients in front of them. Okay. So in other words, I'm not going to be dealing with the U in here in this expression. So if I ask you what is the mass of a proton, you're going to take it 1.00727676 U, but you don't substitute the value of U because we're going to find this expression in terms of U. In other words, what is the unit energy in this case when I take U? So U is again that number in there, which is a big number, 1.66053940 times 10 to the negative 27 times C squared. Okay, so it's that number 1.660 times 10 to the negative 27. This is how much that number is, times 9 times 10 to the power 16. And this is going to be an energy now in joules, because this one is in kilogram and this one is in meter squared per second squared, and everything is going to be in joules, except that I don't want it to be in joule. Actually, I want it to be in electron volts. So I'm going to divide by 1.602 times 10 to the negative 19. So this is going to be actually in electron volt. The answer is going to be in electron volts, because this is how many they are in 1 joule. Okay, but again, I'm going to multiply this number by 10 to the power 6, because I want it in 10 to the in megajoules, not in joules. Okay, so in other words, I want to find what this number is actually in megajoules. Okay, so that's really the whole point of this exercise in here. 10 to the power 6 and 10 to the power 16 is 10 to the power 10. 10 to the power negative 19 and 10 to the power negative 27. That's 10 to the negative, what is it, 8? Is it 8? Yes. Are you guys with me?
Yes.
Okay, so this is 10 to the negative 8 and 10 to the power 10. So that's basically 100. So it's going to be 1.66. That's the atomic mass unit times 900 really, divided by 1.602, and that's it in mega electron volts. So I really need this number because I really need to find it. And if you do the math, you will find that this is equal to 931.5 mega electron volts. Okay, it's not exactly 5, it's 49. Okay, if you do the math. But the point being in here is that this is a good number to remember, that the atomic mass unit, U, is 931.5 mega electron volts. So you don't need to do the multiplication by C squared if you remember this number, okay? For most of your applications in here. So the mass of the electron and the mass of the proton are roughly about 931 mega electron volt, both of them, okay? One of them slightly higher, the other one is slightly less, but because that's the difference between them and the atomic mass unit, that's all. Remember, this is the difference between them. The discrepancy is of this order for the case of the neutron, and this is the difference between it and the atomic mass unit for the case of the proton. For the case of the electron, though, it's a different story. If I do the same calculation, the only thing that changes in here is this expression here. Instead of 1.6606, it's going to be 0.0005. So it's really this number. Or divide this whole thing by 1,836. If I do that, for the case of the electron, it's going to be 0.511 mega electron volt. Okay, it's half a MeV. Okay, so that's basically what the electron is versus the proton and that of the electron. It is a good number to remember for this case. For a lot of this, what is coming next, we use this this convention extensively. Okay. I did not talk about two things in here, and we're going to talk about them later on when we meet on Tuesday. But we're going to talk briefly about them. I want to build two things. First of all, this graph in here that I want to bring your attention to on page 1449, and that is an important graph. If I were, and we're going to do that, okay, to calculate, for example, for the first isotope of the first element that is heavy, namely the isotope of hydrogen, that has actually one proton and one neutron. So in other words, A is equal to 1 plus 1, which is 2, and Z is still 1. So this is the isotope of hydrogen, which is called deuterium. Okay. So this is the highest, the first element. So what I can do, actually, I can do the same calculation for deuterium. Okay. So I can go back to the expression here. I have Z equals to 1, so it's no big deal. I have N equals to 1, so it's no big deal. So I have 1 plus 1 minus the mass of the atom. And if I look at the table that I was referring to, namely the table on page 1445, I have the mass of the deuterium in here, which is 2.014102. Okay. So I can plug in the numbers in here. First of all, the mass of the hydrogen atom, which is 1.0087, first, I'm sorry, 7825, minus the mass of the neutron. The mass of the neutron, I wrote it up in there, which is 1.008 something, which is 6655 minus the mass of the actual deuterium. The deuterium is actually 2.014, 102. Okay, let's do this calculation quickly in here because I need to find this number in here, share. And it leads to important results, of course, this discussion. So I have 1.007825 plus 1.008665 minus 2.014102. And the answer is this number, okay? This is the mass defect for the deuterium. This is how much we're the deficiency, basically, about the case of helium. I really don't want to repeat the calculation. I want to multiply it by that number for the energy. So I want to find the binding energy. So if I want to find the binding energy, all I have to do is multiply it by 931.5. Okay. So there's going to be a mega electron volt already. So the answer is 2.224 mega electron volts. So that's how much binding energy to fuse that proton and that neutron to form my deuterium. But I have two nucleons now. I have two. I have a proton and neutron. So what I can do, actually, I can divide this whole number by 2 to find how much energy it takes to fuse my deuterium in this case per nucleon. So if I divide it by 2, I find the answer is 1.11 mega electron volt for each nucleon I bring to the picture. So that is the bottom line in here is of this discussion. Let me share the screen. To form deuterium, you need 1.11 mega electron volt per nucleon. Remember, you have 2 of them. You have 2 of them. So it takes, each one of them brings that much. And if I do the same calculation for helium, for example, which is the next element, if you wish, in the periodic table after the hydrogen, I will find the number is much, much higher. It's about 7 mega electron volt per nucleon. For helium, it's going to be about 7 mega electron volts per nucleon, per each nucleon. And I have 4 of them, remember. I have 2 protons and 2 neutrons. So I have to multiply this really number by 4 to get how much binding energy for my hydrogen atom. For my helium atom, I'm sorry, for my helium, yes, atom. So in this case, it's going to be what? 7 times 4 is 28 mega electron volt. And if I do the same calculation for example, carbon, which is also has an even number of protons and neutrons, has 12 nucleons, 6 protons and 6 nucleons, I'll find the number slightly more than 7. As a matter of fact, the table, if you look at it, I'm looking at the table on 1449, page 1449. This is how the table looks like. And we're going to come back to this table big time. So of course we started with deuterium because hydrogen, it only has 1 proton. So it doesn't make sense to talk about energy by 1 proton. It's going to be basically it's only 1 element in there. But then, because everything is comparative, so this is the first isotope of hydrogen, and that has 1.1. So it's here, 1.11. So this is the binding energy per nucleon, EB per nucleon. And this is actually the atomic mass A, okay, as you increase A, okay? The table, the graph goes drastically to about 7 for the case of helium, and then drops a little, then goes a little, then drops a little, then it stabilizes and reaches a maximum around A equals to 56, which is iron, and then drops again. So this is how much energy it takes to bind to form a nucleus for every atom. Obviously, the energy itself is multiplied by A. So if, for example, you take 56 in here and you find the number to be 7.8, for example, MeV, it varies between 7 and 8 for the most of the elements, okay? So it's around this number, between 7 and 8, MeV. With the exception of the lighter elements, other than that, most of the time it's in that range. So that's why it's constant. So we really need to understand what's going on in here too. But it starts to drop. And it's very, very stable in here, around 56. Okay, so this is the maximum energy that you can get basically around that point. This has 2 critical things. As I am building up elements from lighter and lighter, I'm getting more and more energy of binding per nucleon, which means I'm getting more and more stable atoms per nucleon. Okay, more and more energy is putting them together, so it becomes harder and harder to break them apart. But then the process from the other direction, if I break these heavier elements, like uranium-238, for example, the energy per nucleon increases. Obviously, it decreases because, remember, each one of them will carry some of its energy, but per nucleon, it gets higher. So that's basically what we're graphing in here. This process from here is called fusion. I'm fusing lighter and lighter elements. This process from here and here is called fission, and breaking heavier elements into smaller ones. And the common point in here is iron. Around that region, basically becomes very costly to break that and bring it down to a lighter elements if you want to do fission, or it becomes not energy efficient to fuse further. So that's basically the whole point in here. And I'm going to end with a little bit of notes on what's going on in the stars, okay? For stars, like the sun or lighter stars, I mean smaller stars in mass, they start in their main sequence life, basically they have hydrogen in their core, and somehow, very, 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 very unlikely, they form this deuterium. And that deuterium later on, once it's formed, it starts a process through which called the, in the case of the sun, it's called the proton-proton cycle that basically goes and forms helium. And this is actually an efficient way of making energy because it's more stable, you release a lot of energy, and the sun basically provides the outward pressure to keep it from collapsing because it has a lot of mass in it and gravity will try to shrink it. But because of this nuclear reaction, albeit it's extremely rare, but it's just enough to maintain the sun from collapsing on itself, okay? And provide outward pressure due to this energy that is released inside the core, and that keeps the sun from falling apart. As long as it has hydrogen inside its core, it's going to do that for a long, long time, for another 5 billion years, basically. After that, when the sun runs out of energy, so it's going to go through the helium. Helium also can make energy infusing and making heavier and heavier elements. The point being in here is that that process is not really a main sequence. The star would have migrated to another version of itself. So it starts to grow, actually becomes a red giant and go through other cycles. But the point in here is the sun will continue making enough elements, carbon, nitrogen, and some of the heavier elements, using this process until it runs out of those energies, basically, inside the core. And then at that point, basically, there is not enough nuclear reactions in its core, so it's going, gravity will win, and the star, in this case the sun, or smaller stars like the sun, or smaller than it, they will collapse and they become white dwarf, and basically they will cool down over billions or trillions of years, so that they will become extinct until they will become nothing. For heavier stars, though, much more massive stars, like about 2 or 3 or 4 times the size of the sun. So what they do, they start also in the similar fashion, except that they are far more rapid because they have a lot of pressure on them, so the temperature is higher, so the process is much faster with them, and they actually start fusing higher helium quickly too. So they go through this process much, much faster, and they start fusing heavier and heavier elements, and they pass carbon and oxygen, like the case of the sun, and they go beyond that until they reach the point when they make iron. At that point, the nuclear reaction becomes not effective, and it's not going to continue. And as a matter of fact, it's going to stop. Once they start making the iron, within a day at most, the star basically completely shuts down in its core and collapses drastically on itself. Okay, so basically the iron, once the star makes it, at that point it's done for. It has signed its own death certificate, basically. Those are the big stars, because it's going to not have enough outward pressure because the nuclear reaction shut down in itself, and there is no more fusion. So in this case, it's going to collapse due to the force of gravity and collapse rapidly. And that collapse actually will bring more and more heat to a point that when the explosion happens, which is supernova, is going to make the rest of the elements. Okay. It's not efficient, but that's during that stage only, during the explosion, where the rest of the elements are formed. So this is basically what's going on, how the stellar stars basically evolve based on their mass through this curve. It's a very important curve. And it's actually, we need to understand it more because we're interested also in how to make energy using fission for nuclear reactors, or actually for nuclear bombs. So we need to understand how this process works. And actually there is prospect trying to harness the energy of fusion. So we need to understand that process too. And we will come up with 2 models. The first model is the liquid drop basically model. We will simulate the nucleus as being some sort of a drop of water, for example. We'll come up with an explanation for the binding energy using that model. And then we will try to go through another one, which is the shell structure model, which is really quantum mechanics. And we're going to visit our own friend the other day that we talked about, namely the particle in a well problem, namely the Fermi sea. Okay, so that's basically the whole thing in here. And we will have an understanding of how nuclear energy is made. And then at the end, we will close the whole chapter with a very important topic, radioactivity. I mentioned already the fact that in the case of the sun, you have the formation of the helium, hydrogen isotope deuterium, and that deuterium actually is not an event that happens often. As a matter of fact, it happens so rarely because of radioactivity. Because what happened in this case, you have a proton and a proton. That's all there is in the sun, in the core of the sun. You only have hydrogens, and that hydrogen, when it comes very close from the other hydrogen, and once they come close and they overcome that repulsion, because they are both of them positively charged, because of the fast motion that they have. Once they come very close from one another, as a matter of fact, one of them changes identity and becomes a proton, in the process emitting other particles. One of them is a neutrino, and the other one is a positron, and also a amount of energy in this case. So the point being in here, that is how the deuterium is formed. And that triggers then, from that point on, once it happens, that triggers the rest of the reactions very fast. and it goes through the process and forms the helium. But again, that is actually radioactivity. The minute I said the fact that neutron changed identity, became a proton, that is actually a radioactive activity. So we need to understand that, okay? That is governed by different forces of nature. So far, we have involved nuclear reaction, nuclear forces, and we're going to explain what those nuclear forces are coming from. We talked about Coulomb force, that is the electrostatic force that is involved big time. And in the case of stars, also force of gravity is also involved big time. But what mediates that, what makes everything possible, what makes everything happen, without it, nothing is going to happen. Stars would not form, nuclear reactions cannot happen, is actually the weak force, the one that is responsible for the radioactivity. So we need to talk about that one, albeit it's weak, but it plays a vital role. Without it, we would not be here talking about nothing, okay? Are you guys excited about chapter 43?
Yeah, I mean, one step closer to finishing the material, so yeah.
For reals.
Is that the reason you're not excited to know about all of these things?
No, I'm super excited. What are you talking about?
Okay, very good. I'm glad that I have somebody who's sharing my thoughts on this. Okay, so I'm gonna stop. I mean, unless you guys have any questions, especially related to the lab or something, we're going to gonna see you
Another
guys on
question.
Tuesday. Yes.
Oh, I don't. Did you already mention when you're gonna post the grades for the?
I did not. I did not post them. I did not actually honestly go through them yet. So I will hopefully will spend some time this weekend on them, and I will post them. Okay.
Also, I don't know. You're probably super busy. That's why. But like, do you know like when you're gonna get like the rest of our labs and all that graded?
Yeah, we'll catch up with them. I graded some of them just to give you an idea of how those things are graded so that you're not surprised at the end. So hopefully you're taking care of all of the notes that I put in there. But I will catch up with them, okay?
I just say
that's
we give
basically-
everyone 100.
No, that's not possible. Unless everyone gets 100, I really don't have a problem with it whatsoever. I'm not, I know I met some people who really have some sort of a bias towards one side of the spectrum or the other. I really don't have that, okay? So whichever ends up, it's fine. Actually, I'll be very happy if everybody gets aces everything, okay? That's going to be something I will tell everybody about it, okay? So I'll see you guys on Tuesday. We have some much work to do, and see you then.
Have a good day.
You too. Let me stop the recording first.